Engineers like to define shape change or strain in a way such that when there's no shape or length change, the quantity is zero. Whereas if there's no stretch, U would be I, and therefore C would be I. So to define the strain tensor, we subtract I from C. So this gives us E equals 1/2 of C minus I, which is known as the Lagrangian Green's strain tensor, or in component notation, its components are del xi, del xr, del xi, del xs minus delta rs. You can see why we've subtracted I from C to get a quantity, a tensor that's zero when there's no strain or no shape change. The factor of 1/2 comes from the fact that this expression is squared. What we'll see later is that the Lagrangian green strain tensor is really a measure of length squared change rather than length change. And that comes about from Pythagoras. Namely, length changes in multiple dimensions, in 2 or 3 dimensions, involve the square root of sums of squares. So in order to eliminate the rotation, we took F transpose F. That had the effect of squaring U, and therefore the strain defined this way has a quadratic definition. And the 1/2 there is so that when we do a Taylor series expansion and linearize, that will cancel.
Let's try an example now. If the components of the deformation gradient tensor F are FIR equals lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3, what are the components of the Lagrangian strain tensor E? So here are your choices. Try working that out with pencil and paper. So let's work this out. E is 1/2 of C minus I, which is 1/2 of F transpose F minus I. So doing the matrix operations, we get that the components of the green strain are 1/2 times F transpose, which is the same as F up here because F is diagonal, times F minus the identity tensor. So this is a simple matrix multiplication. We get 1/2 of lambda 1 squared, 0, 0, 0, lambda 2 squared, 0, 0, 0, lambda 3 squared, minus I, which reduces to 1/2 of lambda 1 squared minus 1, 0, 0, lambda 2 squared minus 1, 0, 0, 0, lambda 3 squared minus 1, which was choice C.
So similarly, we could also eliminate R from F by taking the product F transpose instead of F transpose F. This now, instead of leaving U, leaves V, i.e. F transpose equals VR times VR all transposed, and that's VR times R transpose V transpose. And again, we have R transpose in the middle, which is I, the identity tensor, which leaves us V transpose, or since V is symmetric, leaves us V squared. And this quantity is called V, the Eulerian left Cauchy-Green deformation tensor. So in the same way that we use C to define a Lagrangian strain tensor, we can use B to define an Eulerian strain tensor, which is known as the Almanzi strain tensor. It's sometimes denoted by eta, and eta is 1/2 of I minus B inverse. So if we look at the components of B, there would be Bij equals FIR, FRJ, So that will be if transpose. So notice this time it's the components that refer to the underformed reference coordinates that are summing, leaving us del xi, del xr, del xj, del xr. And notice that this expression is also symmetric in I and j, so bij equals bji, and this time the indices refer to the current or the formed coordinates. Writing out the strain tensor then in index notation, we get that eta ij is 1/2 delta ij minus del xr, del xi, del xr, del xj, which is also symmetric.
Let's work out the Almanci strain tensor components for the same deformation gradient tensor components as in the previous example. If the components of F are lambda 1, lambda 2, and lambda 3 on the diagonal, what are the components of the Eulerian Almanci strain tensor eta? So here are your 4 choices this time: A, B, C, and D. See if you can work that one out. Well, eta is 1/2 of I minus B inverse, where B is if transpose, so we get 1/2 of I minus if transpose inversed. In index notation, this is eta ij equals 1/2 of delta ij minus del xr del xi times del xr del xj, where these are the inverse of the deformation gradients. So this then gives us that the components of eta ij are 1/2 of the identity tensor minus 1 over lambda 1, 1 over lambda 2, 1 over lambda 3 on the diagonal, times 1 over lambda 1, 1 over lambda 2, and 1 over lambda 3 on the diagonal, which gives us 1/2 of 1 minus 1 over lambda 1 squared, 0, 0, 0, 1 minus 1 over lambda 2 squared, 0, 0, 0, 1 minus 1 over lambda 3 squared, which was answer D.
So we'll, in class, expand on these definitions, manipulate them, and give some physical examples.